Good afternoon, everyone. Our next session will be delivered by Dr. H.D. Chandewar sir on design of hydraulic structure. Please allow me to introduce Dr. H.D. Chandewar sir. Sir has done his diploma in civil engineering in 1988 from Government Poly Nagpur, then B in civil engineering in 1991 from Government College Amravati, ME in structural engineering in 1993 Mumbai University, PhD in civil engineering in 2012 from RTM Nagpur University. Sir has worked as structural engineer in Tata Consulting Engineers in Mumbai on various national and international projects like thermal power plants, nuclear power plants, auto industries, pharmaceutical industries, food and chemical industries. Sir has also worked as a visiting lecturer for B and ME part-time degree courses in the academic year 1993 to 1995. Later, Sir entered in the government services through MPSC as an assistant engineer during 1995 to 2008. Then Sir was promoted as an executive engineer from 2008 to 2017. Sir has worked on one major project, 12 medium project and 10 minor projects. Successfully completed one major project, 6 medium projects and 3 minor projects. Sir has also worked in Maha Metro Rail Corporation Nagpur on deputation in 2016 to as a design head. Presently, Sir is working as a consulting engineer on irrigation and water conservation projects, highway bridges come Bandara, liquid waste management projects, hazardous waste management projects, flood protection work, thermal power plants. Sir has number of technical paper published in various national and international journals. Sir has registered 4 patents, published a book on the title of Essential of Canal Structure. Sir also was the committee member of the Handbook on Design of Small Canal Structure by the Government of Maharashtra. Now I request Sir to start with the session.
So good afternoon to everybody. I will uh, I will go with the a case study of one of the biggest reservoir in the India, and the reservoir was raw is a raw water reservoir for industry, and specifically I will enlighten you about the challenges in design and construction. So. Uh, Basically, HPCL, Hindustan Petrochemical and Rajasthan Refinery Limited has entered a joint venture, and they are coming they are coming up with one mega petrochemical projects in the Rajasthan, which is located at Taluka Pachpadra, district district Badmer of Rajasthan. The share of HPCL is 74% and the Rajasthan government is 26%. So it's a mega petrochemical it's a complex in India. The biggest, I will say, it's the biggest petrochemical complex in India, where the product will be HDP. Their product will be the raw material for HDP, LDP, then polypropylene, then and much more PVC and much more petrochemical products. So it's a basically greenfield project having capacity of 9 million metric ton per annum, and the refined project is 25,000 crore, whereas the work of reservoir and allied compounds is of 290 crores. So the area is basically a desert, and the area is established, mostly established sand dunes type. Annual rainfall in Pachpadra is very less, which is about 275 mm. So they're only scanty rains. They'll observe only scanty rains. See, the petrochemical requires petroleum product as raw material, and large scale raw water for the activities, petrochemical activity also, and for the drinking water for the colonies and offices. So the major they require big quantum of water. And as the area is located in the is mostly a desert, and as there is no rainfall at all, the rainfall is annual rainfall is only 275 mm. It's very good rainfall. When it comes to Nagpur, at compared to Nagpur, the rainfall is about 25%. So, so there is no, actually there you won't find there streams, you won't find nala and river in that area. Because rainwater is rainy, because the rainfall is very less. So for this petrochemical complex, then they have to depend on the major dams, because the requirement is very big. So the nearest water reservoir available is the Bhakranangal Dam. The Bhakranangal Dam is at Himachal Pradesh, and which is about 400 kilometer. It is about 1400. It is about 1400 kilometer away from this place. So they have to depend. They have to actually, so the main source of the for the this water is the Bhakranangal um, uh, uh, dam. But the good thing is that the Indira Gandhi Canal is running, which is uptaking from the Bhakranangal Dam, is running um, uh, in most part of the Rajasthan, and is the main source of water for the Rajasthan, this for farming and even for the drinking purpose. But the location of that Indira Gandhi Canal is about 230 kilometers from this area, that from the factory area. So anyhow, they have to take the water from the lift the water from the that from and that location is at Jaisalmer, which is about 230 kilometer from the Badmer, but from this area, from Pachpadra Badmer area. So the main source is from the then raw water from the canal, flowing water. But the government of Rajasthan and the one dam authority told the Hindustan Petrochemical, it's a Hindustan HPCL, to have a 30 days storage for for the at the factory site itself, because they have to close the canal for some maintenance and everything. So for that, then HPCL has to go for their cushion storage for 30 days within the factory premises. And the area is too big actually. The factory is running about in 5 kilometer and 10 kilometer area, and they have allocated about 125 hectare land from this factory near to township. So the task is for the consultant to have a detailed engineering, to have a survey, to have a detailed engineering, have to go with the detailed geotechnical investigation and detailed engineering for the raw water reservoir, having cushion storage capacity of 30 days. So, and from that the my work begins. So, and it was very challenging there, because for any reservoir or for any point of structures, either you require very good quality of soil to retain the water, either underground or above ground. If we are going to construct any reservoir, then it require good quality of soil, but impermeable soil, so as to have a very less seepages. And as the water is coming from a long distance, in 14 kilometer, 14,000 kilo, 1400 kilometer, and it requires lot of it involves lot of transit losses also. It requires lot of energy also, because anyhow they have to lift the water from 230 kilometer, that is from the Indira Gandhi Canal, which is about 230 kilometer, and they have to lift the water from that source, from the Jaisalmer, and to take it to the this factory area, which is about 230 kilometer. And it requires a lot of energy. It is about electricity energy too, for the pumping machine and everything. So basically, the raw water getting raw water at the factory is a very costly affair for this industry. And um, and um, and anyhow, if you bring the water to the factory, then you have to use it precisely, you have to store it precisely. So that's a big challenge, and as there it, at the area is totally sandy dunes, comprises very sandy dunes. So there won't you are not getting any good quality of soil within the premise within the radius of 100 to 150 kilometers. So bringing soil from such a long distance is also a very costly affair for the construction of reservoir. So basically, in this case, the challenges begins actually for this case. So this is how journey starts. So I'm showing you the refinery area here and in township area, and I'm showing the refinery. Now the refinery about 80 to 90% work is completed, and even town or this reservoir also 100% work is completed a year back. And this thing is the idea. The major thing the client was for us was the Hindustan Petrochemical, that is HPCL Rajasthan Refinery Limited, that is SRRL. Project management consultant was Engineers India Limited, Delhi, which is Navratna company. This Engineers India Limited looking after for all these things. They are looking for tendering. They are looking for even site supervision. They are looking for they were waiting proof checking of the drawing, the design and drawing. Design consultant for what this was my company at Hitbonjas Nagpur. EPC contractor is VRC Construction, Delhi. The work was started in January 2020 and was completed in December 2020. This was completed within 18 months because the HPCL and even Engineers India Limited was very keen about the completion of this work. And during this phase also the COVID, the work was closed for 2 3 at least 4 5 months. So it was a big task. Even it was very difficult to communicate. People are working. Even Engineers India Limited were working from home. I am also working from home. And during those period, we have prepared the drawings. We have sent the drawing to the Engineers India Limited that they had approved the drawing, and the work started um, within month two. So this was the challenges again. Edward, health challenges was there during that period. Now the come to the this thing. Now the challenges in the design and construction was it was completely a desert area. There was no soil was available, no water is available for the one the construction purpose because the reservoir involves a lot of embankment works, and for embankment a lot of water is required because you have to maintain the moisture content in the soil, so it has to have a good compaction results. And then not only non-availability of good type of soil, that earthen material. And again the challenge was Bhakranangal dam was about 1400 kilometers from the side. The seepages from the water reservoir, hence, and as the water is the source is about 1400 kilometer, hence the water were getting it in the site where to minimize the seepages in even evaporation losses also. And other challenge was that land piece they have left us for this reservoir is only 125 hectare. So within 125 hectare, we have to complete the huge reservoir having capacity of 37.45 lakh cubic meter. It was it was huge reservoir because the capacity was 37.44 lakh kilometer, and the working period was only 15 months. So within this 15 months we have to do all detail engineering, you have to do soil investigation, you have to do the construction, everything you have to do within this period. So there was a lot of challenges, and we addressed the challenges very nicely. Then come to the quantum part of it, huge quantity. Embankment involvement of embankment was about 16 lakh cubic meter. This was a huge quantity. Huge material was required from the local area. Then we have gone for the different liner systems because the soil was of a sandy type. So to minimize the seepages, we have gone. I have introduced four composite liner system of four liner. Uh, one is geosynthetic liner. It was about 4.6 lakh square meter. Then geotextile liner. It was about 4.6 lakh square meter. Then geomembrane HDP film. It's of again bigger thickness, higher thickness, 1.5 mm thickness, 1500 micron. The quantity was 4.6 lakhs cubic square meter. Then that was a concrete tile works, 40 mm tile works in two layers. The quantity was 9.2 lakh square meters. The total liner system involved is about 23 lakh square meters. That is about 250 lakh square feet and 2.5 crore square feet. Imagine if you are doing tiling work at your house now, it ranging from 1,000 square feet to 2,000 square feet, and still you require 2 3 months to do the tiling and everything work. Here there are the liner system involved is 2.5 crore square feet, and there was double pitching also on the outer side of the burn. It was 1.47 lakh square meter. uh, the another challenge in our design that the entrance, that is the reservoir earthen bund requires some requires some L drains, longitudinal drains and cross drains, same as that of in the dam section. Then external drainage arrangement outside of the earthen one were 15 kilometer. Pump house was there. The because water is coming from in the factory, yeah, that is to be sent it to water treatment, WTP. So um, the the work involves the installation of 850 HP vertical turbine pumps, and the pump house area was 62 meter by 17 meter, and the gross height of was 38 meter. The gross height 38 meter means it was equivalent to 13 story building. So it was a huge, even pump house was a huge, involves a huge work, and the each pump was weighing about 20 ton. So the one design and constructing a building, a residential building of 13 story height is very simple and non-challenging job for the civil engineer. But construction of even pump house of such a big size and of such a height with a loading live loading with live load of 1 ton per square meter like this, and even the load of EOT crane, load of pumps and walls. It was a big job. Other challenges were that the Badmer area was it's coming in zone number zone number 3, and the reservoir side is very close to our enemy country. It is very close to enemy country Pakistan. It is about 100 kilometer. So this thing, the safety and stability of the reservoir and everything was again was a very crucial issue. So this thing, uh, again the dam height was about, earthen bund height was about 10 meters. Storage capacity is about 10. Storage capacity was more than this one. As the dam height here was 13 meters, that is about, which is more than 10 meter, and as the storage capacity is more than 10 lakh cubic meter, because our storage capacity was 37 lakh cubic meter, which is more than 10 lakh cubic meter, and embankment quantity is more than was about 15 lakh cubic meter, which is more than 7.5 meters. So this reservoir is to be designed as a large earthen dam. So the theory we have used for this design of the reservoir are from the various provisions as laid down in the IS 8826, which was used for design of large earthen dam. So these were the challenges. Other critical challenges were here that Rajasthan is very hot area. Even and again it is a daytime it's very hot and night time it's very cold actually. Even if you will go to in even May and April or June, you will find the day temperature about more than 50 degrees Celsius and night temperature about 14 degrees. Night temperature even just after the 7 8 p.m. it is getting very cold. So laying the geomembrane, because geomembrane is just a HDP film, laying a geomembrane in a such hot and cold region is a very difficult task because it's getting wrinkled. The HD film getting the wrinkles are getting on the geomembrane. Then because of getting wrinkles in the geomembrane, it's very difficult to lay the tiles or the concrete tiles on it. So then, the in such cases, the geomembrane we ask them to lay geomembrane at even in light itself. So that the work was going. some work was going, day and night the work was going. So then they have then we have decided the priority and the even the phases of construction phases to do to execute the work within stipulated time. uh, there were expansion and everything, lot of difficulties were there. uh, Now these are the references we used. One is IS 8826 design, the guidelines for design of large dam, large or oblique and rockfill dams. Then this IS 12169 we have used again for some components, small embankment dam. Then IS 7894 we have used. Then we have used the guidelines of the Central Design Organization of Government of Maharashtra. And then we have used the again we have used this thing 1893 is a regular code for earthquake distribution, and IS 9452 for the to measure the seepage losses. Then we have used IS 1498 for the classification and identification of soil for general engineering purposes. Then we have used IS 2720 for the core sand, soil and other materials. And then we have used referred IS 8237 code of practice for the protection of slope for reservoir and embankment. We used 7784 part 1, part 2 also, the code of practice for cross works. And then IS 5050 for relief wells. So these are the codes were used for the or design purpose. Then again other cases are 14750 for seepage measuring devices. Then another code is there 10635 for guidelines for calculating the freeboards and requirement of dam. Then IS 14690 for quality control of earthen dam. Then CPCP guidelines we use for the which is basically for the landfills which are drafted by the IIT Delhi. We use for the different type of liners. Then CPCP guidelines also we use for the quality and consumption of various liners also. So these are the codes we refer for the design. Now, these are the basic background I have told you about the various challenges and about the challenges in the issue, getting the challenges in the getting the challenges for the actually regarding temperature also, rainfall also, getting good quality soil, getting water from the nearest area, nearest locality. Now, before I go in details, I will take you to the site with a small 5 minute video. So just will go through this video. Start the So this was a site, this was a land piece of land made available by the HPCL to the for the reservoir. This was the actual situation before start of the work. This is the schematic layout. You can see in the with respect to north. It is like you will see these are the two ramps. Actually, this reservoir is like we are designed as a pond. The length of this pond was about 1200 meter, 1.2 kilometer, and the width is about 0 0.6 kilometer, is 600 meter. And the whole this thing reservoir were divided into two compartment, compartment one and compartment two, and the on both compartment we have provided a RAM because on those in those area na, because it's a sandy area and lots of sandstorms are coming, so it may have to remove the silt and sand after the once the sandstorms are gone. um, so for that case we have divided the horizontal two compartment. It can be made our the silting can be done from any other compartment, and from other compartment any water can be lifted. So ramps are provided, permanent ramps are provided in the for this reservoir in each compartment. This is during the execution. You will find this. This is the earthen work is going on. This is the pump house location. There are two. This is satellite image actually. Now the earthwork is going on. The ramps, the earthwork ramps are also going on. So then again, you can see the earthwork how this drone image during the execution, and this you will find this is the this thing there. Uh, Other embankments work of other embankments going on. So the now the typical section for the northern burn is like this. Uh, this is side water side. This is outer side. You will find these are the toe drains. These are the internal drainage arrangement, drains, and then they were provided as a cut off. And this orange color is seen is a sandy soil. So these are the parameters. Finished bed level was like 102 from this is mean sea level. Then mid worm level is 107.85. Maximum water level was 112.85, and then road top level was 113.85. Minimum upstream slope and downstream slope, the workout is 3:1. As per the code, the minimum required slope was 2.5:1. Top feet of the burn we have kept 11 meter because this is for higher side we have kept because some of our utility was going on the burn, and they required us two minimum two lane roads, and the client was in need of two lane roads on the this thing reservoir. So the minimum required width as per code is 6 meter. We are going with go with 11 meter. Then berm interval as per the code it is 12 meter, but we require to provide the berm at 5.5 meter for the stability point of view. Freeboard as per the code 1.5 meter freeboard is required over the maximum water level. We have provided freeboard 1.5 meter here. Maximum height water to be stored is 10.5 meter. Maximum height of earthen bund was 11.5 meter, and maximum height of earthen bund from to RCC parapet. We have provided RCC parapet also on the bund. It was of 13 meter. Though now the main work was to finalize the soil type and the location of the source of the soil, you can say quarry. So what the probable site within very close to the factory area were visited. Uh, the PMC then consultant EPC contractor. We have finalized 21 survey numbers of the from the village Khasra numbers selected for testing, and from each survey number we have sent at least three samples per quarry taken from the depth of 1 meter, 1.5 meter, and 2 meter, because the soil testing here is a critical job, and the selection of proper soil for the embankment is a very critical job for the reservoir. So how good intensively we did geotechnical investigation from the probable query. And then the other thing is that for reservoir, uh, we require to do the grains analysis, then sinkage limit, we have to find out the sinkage limit, then plasticity limit, liquid limit, and plasticity index. This PI is very important for us actually, for the design of earthen pond. This PI is very important for us. Classification of soil is also must. Field and dry density, including ODD and OMC, required. Cohesion and friction of the angle of repose is also must, and permeability test. These all tests we have carried on all samples. Then out of 11 quarries, we have rejected 10 quarries because the soil. Why 10 why rejection? Because of this reason. Soil is of SM type, because the SM is not actually, code is not allowed. This code is not allow you to go with the embankment with the SM soil. Then cohesion is also very less, 0.01 kg per square centimeter. And permeability also very less. Then plasticity index say was PI was nearly nil. So we have rejected 10 source for the of the soil, and we accepted out of 21 we have accepted 11. And this because the soil there was of CL type clay with low plasticity, and CS type, that is clay with high plasticity index. You might have learned about all these things in the second year or third year about this in soil mechanics, the grain cell analysis, then classification of soil. These are playing very important role in the design of earthen bonds actually, earthen hydraulic structure, not for the road structure or thing, but for the reservoir. These are very important. This plays very important role. The classification of soil, then PI, liquid limits, plastic, very plays very important role. Cohesion here is about 0.25 kg per square centimeter. Permeability was not so good, very poor, but anyhow, we have to go with this soil because at least they have at least qualified some codal requirement. So we have to go with the CL and CH type material. K is very less, but anyhow, we have to go with this material, and hence because of this only we have product four composite liner system on inside of the embankment to reduce the slippages. Plus index was for the plastic index for the CL type was 15. It was PI was more than 15, and for CS it was more than 28. Maximum dry density was 1.75 gram per cc, and angle of was very poor friction. Angle of was very poor also. Now, as there is desert type, getting good quality and clay material is the prime requirement for the earthen, but is a big challenge for the design construction. But still, we have to go with the reasonably good material. And as the uh, good quality clay was not available, we have to go with the homogeneous dye type earthen bond. Normally, or in India or any in the state, we will go with the two multi-zone earthen bond for the any reservoir. The halting portion is of brick black cotton soil or very clay soil, and outer side is a like murumious or casing material like murum or sandy soil like that. But as here in that area, that we're not getting a good quality of clay soil, we have to anyhow we have to switch on for homogeneous dye type earthen band. So and then further it is different than design criteria. And then code has given the code 18826 region of earthen dam in appendix A has given the suitability of the type of soil. That was clearly mentioned for when you're with GC, if the material is for homogeneous, when the material you find is GC, then it's very suitable. And only suitable criteria CL and CACI, and fairly suitable CP, SM, and SH. So CH. So my soil is of suitable to very fairly suitable type. So I have to go with the CL and CS. So my now dam, my earthen bund there constructed there is from the soil of CL and CS type, and it complies the code requirement. And the other requirement was that for CL type soil, your PI plastic index should be more than 12, and your and but in my case it was in my case the CL was more than 15, so it qualified the code requirement. CS material, the requirement for the code requirement is that is the PI should be more than 20. In my case, in our case, PI was more than 20. In so the material was chosen for the embankment, that is CL and CS qualifies the quota requirement. Hence, we have gone with this two type of soil. And another thing is that now we come to the design of earthen bund. So basic design requirement is your earthen bunds should be safe against the overtopping. It should be safe against the stability. That there's bund slope shall be stable enough, and there should be arrangement to dissipate the internal seepages. Internal seepage should be much less, but whatever will be seepages, it should be drained out properly. So for the design of earthen bund, or the design of reservoir burn, or the design of earthen dam, you have to go for with the three type of safety issues and guidelines. So then another first one is what the overturning. Your water should not be get overtop to the earthen burn. So we always go with the minimum freeboard criteria. The maximum water at the top of the burn is always we keep more than 1.5 meter above the maximum water level in the reservoir. Correct. But this is not the case. You have to find this is the minimum case. It should be minimum 1.5 meter above the maximum water level. But anyhow, you have to calculate the freeboard requirement with the coder requirement. So freeboard, so it depends on the criteria of freeboard, depends on the height of wave generated at the on the water surface, which is worked out, and which is worked out here is a 0.90. You have to, when there is the design wind will be there, or will cyclone period, the waves will be generated on the surface of the reservoir, and hence you have to calculate the wave height, maximum wave height for the design wind velocity, and for the depth of water, for the design depth of water, and average phase distance. So in this case, our wind velocity was about 120, 170 kilometer per hour, because it is very, that area is very flat terrain, and very close to, it is about 150 kilometers from the sea level, and no forest you will find there. So there the cyclone wind velocity is about 170 kilometer per hour. Depth of water here, again the wave height depend on the depth of water. Maximum will be the depth of water, maximum will be the wave height. And average phase distance here in case was 53 meter. More will be the phase distance, more will be the wave height. You might have learned in the newspaper and even the TV that during the cyclone and during monsoon, you will find in Mumbai coastal area or Nariman Point, you will find the 3 or 4.66 meter wave height in the sea. So that any civil engineer can calculate the wave height, considering the wind velocity, depth of water, and average phase distance. In your case, we have worked out the wave height as 0.9 meter, and we have to multiply it by, we have to keep factor of safety as a 1.5. So in that case, zero point 0.9 to 1.5, our minimum freeboard, our design requirement for the freeboard was 1.35 meter. But as the code said, you have to provide anyhow the freeboard, anyhow you have to give the minimum freeboard for the such dam is 1.5 meter. So we have gone with the 1.5 meter. But we have did all these thing, we have had calculation, everything. The code is there. You have to, also you might have learned in the your irrigation engineering. So that was about the, if you have provided sufficient freeboard, then there won't be overtopping. Hence, your dam is always your other bund will always remain safe against the overtopping. Second safety aspect was safety of reservoir with respect to stability of burn. Your burn should be reasonably stable during various operational conditions. So you have to provide the top of the width of the burn, and the side slope of the burn, and even the berm height and berm interval, such that your overall earthen burn should be stable. The overall slope of the burn should be stable. So there is again laid down theories in the codes. So I have gone with there are again the safety, this stability of the burn. There are two different cases. One for the stability. You have to check the stability of the burn for on upstream side for different operational condition. Then for downstream side for different operational condition, because the condition is different for downstream and upstream. Upstream you have to retain the water. Downstream you have to drain out the water. Downstream slope is subject to only rainfall and this thing, some seepages. Upstream is Upstream slope is subjected to sudden drawdown condition. Upstream is subject to very this thing subnet condition in the. So there are let down theories in the course. So what about that? Uh, then shall be erosion. Then again upstream sword and even downstream sword should be safe against erosion due to rain. So that upstream slope should be safe against the erosion by rain and even wave action height due to wind. So that much that everything you have to the treatment and accordingly to the treatment you have to provide so as to avoid the erosion and damages due to rainfall or even the wind waves. So there is now let down theories in the books and even code. There is code also. So okay, Swedish sleep circle we have used which is based on 7894. We use the Swedish sleep circle method for the stability of slope. So they have given six cases actually. There are different cases. Construction of you have to check your the reservoir bund for the these all six cases, but may not your these all cases may not be valid for even you know uh, every reservoir. In our case, case 3 is valid for upstream slope and case 4 was valid for downstream slope. Case 2 is reservoir with full condition and case 4 was this was for case 2 was reservoir with full condition for upstream slope and case 4 was steady seepage for the downstream. These were the two conditions which are for which we had to we did calculation stability calculation and accordingly we have put the slope of the this thing up bund. And the sixth one is earthquake condition. You have to check the even all above cases, section case 2 and case 5 for the earthquake condition 2. So we did these two cases for non-earthquake conditions, case 2 and case 4 for non-earthquake and earthquake condition. So this is the method how to go with the sleep cycle. Just I will skip within 2 seconds this sleep. There are n number of you will find n number of sleep circles. This is one of sleep circle starting from the edge of the top of the bund. Then this thing this for upstream slope. I'm talking about upstream slope. Second one is the sleep circle with tangent to the dam seat. Then again, third one is the sleep circle starting from the mid width of the dam, and fourth one is the then again from this edge of the berm, fourth one. Then again another is from the toe of the sleep circle starting from the toe of the upstream slope. Then another is this is starting this is tangent to the this is just tangent to the again um, this thing embankment. Then the slip circle 7 is for downstream slope. Again, the slip circle start from the outer edge of the bund top. Then second one is starting from the which is tangent to the dam seat. Then third one was starting from the mid width of the top width of the dam. Then next one is the slip circle starting from the inner edge of the berm. So there are n number of, but as a designer can decide which are the critical sleep circles, and they have to and then with all these critical circles, we have to find out the sleep circle, we have to find out the required factor of safety. So in my cases, in if you consider if I for the upstream slope, north non-earthquake condition for north earthquake condition, sleep cycle C1, the my factor of safety was 2.28 against 1.3. For C2, factor of safety was to 1.52 against 1.3. Then like this, you will find that these are the right one is the factor of safety and this is minimum. Everywhere my factor of, because for the slope of 3 to 1, I have taken 3 to 1, but for 2.5, 2 is to 1 and 2.5 is to my both slope, outer slope and inner even outer slope and upstream slope and downstream slope was found unstable. So at the last I have gone with the 3 to 1 slope. For those conditions, these are the factor of safety and the minimum requirement. Now we'll find that in earthquake condition, I just see the slip circle C3, the minimum requirement is 1, whereas my value is coming 1.0. Just it is just find is just you find just is safe. And next come find just to see the C2. The minimum requirement was 1 factor of safety was 1, whereas my factor of safety calculated sector is 1.01. So that means I have gone with very critical design. I mean, I have not seen any. I have not given some oversized section there. So we'll find that bilkul neck to neck. I have designed the. I would provide earthen section neck to neck, because my job is to within 125 hectare. I have to give them optimum size of the dam, optimum height. I have to give an optimum storage capacity. You know? And their requirement of storage capacity was 37.44 lakh cubic meter. So within 2125 hectare, I had to do all my business, because flatter. If you go with the flatter slope, then my bottom width requirement was more. Even my storage requirement was less. And if you in such cases, then I have to increase the height of the earthen barn. Then again it's a very costly affair, and again stability issue. So my job was to provide a most optimum design for the client. So the same case is the downstream slope also you will find. Downstream is very kind, you will find very stable in the earthquake condition and also non-earthquake condition. That was the requirement was for the minimum factor safety was 1.5 here, and for earthquake condition minimum factor safety is 1 meter. It is here we will find it comfortable. So this is how one is overtopping issue was resolved, and second was the stability issue was resolved. Then final recommendation was my recommendation was slope 3:1 is found for the upstairs be stable and hence adopted. Cohesion of the soil we have now, because from the 11 source we have finalized these things, material type and everything. Then we have asked them to procure the soil from those quarries only. And this how actually when then we have, as a designer, we have to freeze all these parameters. So my first parameter that I have freeze the parameters. I have recommended slope 3:1 for upstream and downstream. Then I have recommended cohesion of soil, it should be more than 0.25 kg per square centimeter. Then I recommended soil type CL with plasticity index always more than 12, and CH material CH with plasticity index PI is more than 20. And this had to be checked periodically, daily and weekly. They have to check these thing all parameters, and then only, and they have to keep a record, and then only will say that the constructed dam is stable. Then value of cohesion and all type CL and CL shall be being used, shall be checked weekly, and record against shall be maintained. So that was the recommendation we did, we have put in the our design report. Then come to the seepages. No, the seepage should be very should actually be, as the sand, as the material we have is very sandy soil, and then to minimize the seepages, we have one for we are recommended composite liner system. So upstream liner system was for this thing. This system composite is safe against it minimizes the slippages. Also, it's safe against the erosion due to rain and water waves. Right? So downstream slope protection was of the pitching only, because the pitching we have provided 30 mm, 300 thick dry rubble pitching. And this treatment also protect, this treatment protect the slope against the erosion due to rain and avoid the bushes growth also. Rubble pitching shall be hand placed. We told them that it should be hand placed, and it should be of sound hard rock, 150 mm to 300 mm size, with hand driven wedges and chips of smaller sizes. So that was the main requirements for this. Then come to downstream slope protection also. Uh, we have recommended soot drains at the soot drains along the slope at every 30 meters, and we have recommended even catch water drain at the berm level. This is, you see, the berm level we have provided catch water drain and the soot drains like this. This was the section for the catch water drain and soot drain. So then again third aspect was safety of reservoir with respect to seepage control. So your amendment should be embankment fund should be such that as to control the piping also. Then your embankment and foundation should be such that it should avoid the piping. You should avoid erosion, you should avoid sluggishness, you should avoid excess loss of water. And for which we have made the following provision. Liner system we have provided on Austrian side, then laminar drains within the earthen body, then cross then were provided within the earthen body, then doctor were provided on the toe of the outer toe of the this earthen embankment, then toe then were provided along the periphery of the this reservoir, and we have provided one relief well. These are relief well, and this thing this helps to monitor the health of the dam reservoir. Then okay, startup is very there. While liner system is recommended because it was a good quality of impermeable clay is not available, so we have to go with the sandy type soil CL and CS, and with the homogeneous dike type strategy in the embankment. Then strata very sandy type. Then sweet water is sourced from the Indira Gandhi Canal, which is about 230 kilometers from the source from this factory area, and the parent source is of Bhakra Nangal Dam, is about 1400 kilometers. So and desert area has a very scarcity of sweet water, and you won't get a sweet water actually. You will get some water there, but it's very salty water you will find in those areas. So continuing these stringent provisions for the or safer provision for the liner system we have gone with. So liner system here, the composite liner system comprises top layer of of concrete PCC concrete M20. The tile size was about 400 mm by 200 mm, 50 mm, to be laid in cement mortar 1:3. Next layer is of M20 again, tile of same size and mortar. It was to be laid in the mortar with a mortar 1:5 cement mortar. Then below that SDP liner of 1500 micron, that is 1.5 mm thickness. Then below that geotextile liner, and below that geosynthetic liner. And geosynthetic liner, so that means we are first on the earthen compared profile. We have first provide geosynthetic liner or that geotextile liner or that SDB liner. Above that, two layers of concrete tiles of 400 mm by 500 by 50 mm thickness. So these are the composite liner system we have put on the scene. This schematic diagram I am showing you. You will find out this thing everything compacted surface. Then you will find this thing geosynthetic liner, then geotextile uh, liner, then 1.5 geomembrane. Then at bed we have provided one additional layer of this sand layer, but slope we are not provided because it's not advisable to provide a sand layer there. And the sand layers to have the cushioning effect, because during the deseating this all small trucks is going to run all on the bed of the, so we have provided some cushion to the line. This is ties. So then again this is the two ties layers we will find here. So these are the type this is this liner system we have recommended. And then again, the another aspect for liner is that it should be well anchored at the top of the bund. Otherwise, because the tendency of liner is to slip it down. So in most of the cases, people come to from all over Indian themselves because of some because of some reason, or liners are getting slide down, and over this thing. Over the case, then when the Ispat plant they came to me that within a year our lining system collapsed. So because the most of the designer doesn't know, they only just apply the basic knowledge and they just recommend some liner system, and even they do not go for the proper anchoring to the at the top of the so in that case liner gets slips out because the liners are very friction, they are no with very less friction, this HDP and geosynthetic liner. So to properly anchor it, so the anchor trains were provided. This you shall see the photographs of some tiles and some these are some these curing burns are there. Lining burns going on different this thing. So this you will see the white color is the geosynthetic liner, then usko HDP liner, then black one is HDP liner you will find here. And then these are the our runners, some profile walls. We say it is a profile wall. Before going with the for the liner system, even for laying a liner, we go for we always go for the this thing profile walls with a particular end, and then we fill the gap between this profile wall by the tiles. So you will find these photographs of the liner system. Then you see this how the system is going on. Some laborers are laying this thing tiles, and another people are filling a joints, mortar joints. So this is how the work is get got executed there. You will find this curing pond also. You find there will find in the bed is so na 1200, it is about 1200 meter by 600 meter bed is it's up, so it's huge area. So liner always go with the panels, some 16 meter or 20 meter 30 meter panels. So mm, then curing system also, they have good curing system also there. So about next to control the seepage control by subsurface drainage. So when any other element subjected to the water oxygen side, in due course of time, you will find this is seepage line. We will call it phreatic line. We will call it a phreatic line. The gradient is about this phreatic is 4:1. Sandy soil it ranges from 1:3 to 1:5. Normally for design purpose, we do it. We take it as a 1:4. This is the phreatic line. The earthwork below the compacted earthwork below the phreatic line, you will find it is very you will find is a very submerged condition. So during the stability analysis, we do the analysis considering this is the submerged soil below the phreatic line and above is a wet condition or dry condition. So this is phreatic line. You will find wherever it touch to the dam sheet on the downstream side. From there onwards, you will require to provide a drainage system within the earthen bed. So you will find there are there two three types drainage system. One is this thing tabular type. This you will find this is a longitudinal drain. Then this is from this to this toe drain, which is we'll say it a cross drain, and this is rock toy portion. Again, rock toy also there is, they will find two three layers of filter material and this toe drain. So it is elaborately explained in the further. You will see this is the entrance. This is along this along the periphery of the earthen bund on the downstream side. This is phreatic line, and from this to this is the cross lines. You will find here is a this filter material different type, and then again this is a rubble plug, and this again rock toe. You will find rock toe again it will with the filter material and the store drain. Downstream pitching, you will find downstream pitching. This is soot drain. You will find soot drain here. So now you come to plan. You will find this is the entrance within the earthen bond, right? And this is causes the making about 40 angle. It makes angle about 45 angle, and this is how the seepage from this to this area is getting collected to the toe drain with through the cross drains. So this is how the general arrangement for the drains, the entire arrangement for the drains. Then there are different pictures. I will show you all the different pictures, photographs during construction. This is you will find this is the open road and this runs along the periphery of the one, and the seepage water is getting collected at the lowest point, and then it to drain out to the lowest low-lying area or low-lying area. You will find this is cross drains, and then you will find it is soot drains, berm, and these are this is catch water drain and this is soot drains. And liner system, you will find is white color, gray color. These are the liner system is going on. The work of liner system is going on. And this is that pump house. You'll find this is that pump house within the body of reservoir. So longitudinal, this is the typical cross section of longitudinal drains. So it is in the book, and even you will find in the irrigation book and in course also. So then this is again a catch water and water part provided at the top of the bund, um, because roadside and it is getting discharged to shoot drains. Then this is cross drains, crossing of cross drains. This is a typical cross section of toe drain, the typical cross section of toe drain. Width is minimum 1.5 meter, then the minimum depth is 1.5. This is the total requirement, and we have provided VNOS in a particular interval to measure the seepages. We have itself here actually, a lot of places. This is the actual photographs of this is toe drain and cross drains. Actually, this is to be protected by the rubble pitching, but that to be grouted partially, because the grouting is only required to hold the rock in position, but each and every joint we are not plug it by the grouting, because we have to allow the seepages, whatever the seepages within the earthen band, we have to allow it to we have to allow it to come to the toad and pause there. So it is partially grouted actually. uh, this is a good typical section of this rock toy. You'll find photographs of rock toy here. Then this is the typical um, cross section of the relief well. In for relief well, we have gone for the 200 dia slotted pipe are surrounded by the filter metal of geomembrane. These all provisions are as per the codal requirements. So this is what seepage measuring unit we have provided, VNOS we have provided, we have given start also. This is VNOS added 200 to 250 meter at the interrupt 200 to 250 meter we have provided VNOS just to measure seepage, because this is the only unit we can check the health of the dam. We have to periodically we have to maintain the we have to keep the record, we have to measure the seepage weekly basis. We have to keep the record, we have to observe whether in for some period there will be some abnormal seepage or there or not, or normal seepage are going on. If you find abnormal seepage at particular venous, then you can locate that this part is something is a which need some repair or some rehabilitation works. So this is how the venous were observed. Now we'll find the running works of the earthwork is going on. And the soil type, it was stricter this thing instruction at the for the side that the soil they are bringing from the notified quarry, they have to check weekly on weekly basis that your soil shall be a CL type and having PI more than 12, and or the soil shall be of CS type having PI greater than PI, and the poison should be more than 0.25 kg per centimeter. Weekly testing is required from the client side also, from the quality QC side also, and if you they found that if the material is not up to the mark, then they have to close that quarry and they have to bring some another quarry. That was the um, protocol was issued for the site tour. And the field density, the compared density should be there, but the again stringent criteria were issued for the site people that the density shall be more than 95% of the proctor density. So before going for another layer of embankment, they have to check the newly constructed layer of the embankment and to find out and to see whether they got the density, field density more than 90% of the PDD. So that was stringent criteria. If it is not found, it is not less, then you have to go for the compaction. You have to ask this roller person to have a more passage of roller on that, so as to have the field density more than 95% of the field high density more than 90% PDD. So this was the stringent issue, and the embankment shall be in layers of 25 to 25 centimeters only. We allowed ask them. I have actually drafted some protocol for the embankment, and clearly told them that the thickness of the layer shall not be more than 25 sorry 25 centimeter. So and the compaction was from by two types of roller. One was from the seepage the seafood roller, and another time the static roller. So the contractor has brought this type of seepage roller. You will find the seafood roller, the seafood roller. Because seafood roller, a lot of good quality of kneading action it took place, and it helps to have a good density during during the execution. So this was the protocol we have to maintain and during the site. This again you will send this thing. This is the middle burn of bifurcating two compartments. The you will find earthwork quality of earthwork there. You'll find also the simultaneously the work of pump house and sump was going on. The This is the sum 16 meter long and 12 meter width. and the depth of height of the sump was 18 meter. And then again you will find that this is roller arrangement we have provided on the excavator. This is a specific arrangement, mountain arrangement for the on the excavator for this compaction of the slopes. So contractor deployed this machinery with this arrangement for the slope compaction. Then there are some protocol adapted for the keying of different layers, because at a glance, at a time, and every time it is not possible to have a have embankment of embankment for the whole section. So contractor has to go for the he has to take for segments of 500 meter or 200 meter, and but then there is a keying issue. So we have adopted some protocol that this of toothing exercise benching shall be done. If this portion is for the all executed embankment, and this new embankment, then for the best for the proper king they have to go with the benching with the benching in the old embankment. So these are some photographs. Some pitching work is going on, and the lining work is going on. And then this is also ramp. And then there are photographs. Now here you will find the most of the lining inside lining is completed. Outside pitching is completed. And even road tarring is also over. And this roadside this pure block they have they pure the surface also. This is you will find the now the completely done, actually completely over lining, all inner linings is completely over, and some pitching work is nearly completed. You will find this is this pump house. This is a small. You'll find a small image, but it's a quite high pump house. So these are some photographs during this side view, and this is the completed. They have tested this reservoir for 3 4 meter height, from taking bringing water from the local some source, because salty water they have tested with the salty water actually. Now the whole system is under with this thing, this pump house at Bagundi, that main source is also ready. But at the industrial work is not completed. They have not brought under operation the reservoir, but they have tested the reservoir. They have tested. They have 5 6 meter. They have. I have some photographs. You will find these photographs. Then you will find these photographs with water. You find these photographs with water. So this is how the work has executed. Now this is about the features of compose. Some compose is about 62 meter in length, 17 meter width, and 37 meter height. They have 10 bays of 4.5 meter, and then 8 pumps has to be installed. Now initially they have installed 4 pumps, and they have made a provision for 4 pumps in future. So EOT crane was of 20 ton capacity. So this is you will find. Then there are different features of purpose. I will not go in detail because I think time is nearly over. Okay. So this was layout of pump house. This was layout of pump house. Then this is again a layout of wall floor level. Then this was some this thing some and this thing. This is the cross section of pump house. You will find this with the EOT crane. You will find this pump house, and this is 1838 meter, 37 to 38 meter high. And this is from photographs of raft of the pump house. Complete raft. There is no activity resting on the sandy soil. SBC was not more than 20 ton per meter square. And no hard rock available there. So we have gone with the raft. So then, and this is again the photographs of during construction. This is the pump some. They use some 62 meter length, 17 meter width, and about 19 meter high. And then these are allied pipelines were going on. These are allied pipelines. This also our design. Then now the pump house is sufficiently. At the it is at roof level now. The work is at roof level. So erection of pumps are going on here. You'll find the erection of pumps are going on here. Then now this is finished product. You'll find this 4 pumps of 850 HP pump, 850 HP. you'll find this 20 ton EOT, and this height is yeah, 16 meter. There is again one floor layer below this floor, that is wall floor layer, is a 4 meter. It's about total above the ground it is about 18 meter, and below the ground it is 18 meter. So this is how work executed, and this is the other aerial view of pump house. One again, this one side is sodium hypochlorite. This is there is a tank of sodium hypochlorite. Before sending the water to WTP, they have to dose the give the doses of sodium hypochlorite to the this thing, the running pipelines. So this is the evening photographs of the pump house and this thing. So this is how the my presentation over. If questions, if any, are welcome.
Anyone having any questions related with the structures, hydraulic structures? Yes. Okay. Thank you, sir, for your
Okay.
informative session.
Thank you very
Thank you.
much. Thanks a lot.
Thank you, sir. Thank you.